Welcome to another video in our course on probability theory. Last time we had Poisson convergence, and today's one of the highlights of the lecture, which is the central limit theorem. You know this already from the theorem of De Moivre and Laplace from your basic probability course, and today we will learn about a more general version of the theorem, which deals with the so-called Lindeberg condition, which gives you a precise condition when convergence to a normal distribution holds. Let's see. So, we have the central limit theorem. Let me start by stating the result. We have, again, as we did last time, such a triangular array of random variables. So remember what that was. There was a picture like here. So we have infinitely many rows of random variables, and each row has finite length, but the length increases. Again, we have that within rows, random variables are independent. We have a random variable which is normally distributed with parameters mu and sigma square. We have that the sum of expectations along one row converges as the row converges to infinity to mu, and for the variances the sum converges to sigma square. And then the interesting part of the theorem that I show here is the direction from 2, which is the so-called Lindeberg condition, which I mentioned in the introduction, to the first part of the first item here, which is the convergence of the sum of the random variables along each row towards x, which has the mu sigma square normal distribution. So that's the interesting part. And if you add a little bit to the first item here, this convergence of the suprema of the variances, you even get that these two conditions are equivalent, which is of course also nice to have, but in implications you don't really need this. So, okay, what's a bit strange here, which you do not know yet, you have this triangular array of random variables. What you know from the basic probability course, maybe, or at most, you know the following. You have a sum of random variables. So the x case is not a triangular array, but it's just a sequence of random variables. You sum them, you normalize them, so you subtract the expectation and divide by the variance of the sum, as squared with the variance of them, and this here converges to the normal distribution. So how does this fit into the framework that we just had? And let me discuss this. So if you take mn equals n, and you take xnj equals xj minus mu divided by square root n sigma square. So that's the connection basically. How you come from the sequence of random variables to a triangular array with mn equals n, so it's perfectly triangular. And I claim that these x and j's now fulfill the Lindeberg condition. So, okay, of course, the expectation of an x and j, that's the expectation of the numerator, which is 0 by construction. So the mu equals 0. The sigma square, what is this? So we had here, yeah, the sum of these variances here. So variance of this thing here is 1 over n sigma square. Yeah, and you divide also by n sigma square root. So the sigma square from that I get here is 1 when I calculate this sum here. And if I now am able to check the second property, the Lindeberg condition, then I know convergence to the normal distribution. So can I get this? And the answer is yes, I can get this. Let's see. So Lindeberg condition involves sum of squares, x and j square, on the event x and j, absolute value is bigger than epsilon. Well, and you can use the Chebyshev inequality, basically. Well, so we have mu equals 0 and sigma square equal 1, so there's no need to subtract 0 here. So I don't need this here. Yeah, like this here. So, and what else do I need here? So the x and j's along each line there have the identical distribution. So this here equals n times the same thing for a single one. N times the expectation of x n j square. Yeah, so this here is square. What's the expectation? Well, I can pull out here 1 divided by n times sigma square, n sigma square. And I get always the same thing, x1 minus mu square. And I'm having this on the event that x and j is in absolute value bigger than epsilon, which means I'm on the event that x1 minus mu, okay, absolute value I shouldn't forget. Oops. Absolute value is bigger than epsilon, and I'm bringing the square root n sigma square on the other side, like this. Then I see that the n cancels. And then I see, well, this here has a final expectation. But as n goes to infinity, this thing here goes to infinity, which means this here converges to 0 pointwise, and there is a dominated function, which means by dominated convergence that as n goes to infinity, this here goes to 0. And we have shown that the Lindeberg-Feller condition holds, which, using this theorem here, assume we have proved it already, means that we have convergence to the normal distribution. Okay, that was the first remark on this corollary. The second remark is that the Lindeberg condition sometimes is hard to show, because basically, yeah, we're dealing with this kind of strange event that something is bigger than epsilon, and you have a square here, so it's maybe a bit difficult. But there's an easy to check condition which is stronger, which is called the Lyapunov condition. And from the stronger Lyapunov condition, which means that the sum of moments which are higher than 2 converge to 0 in some sense, from this the Lindeberg condition follows. Let's see why this is the case. Indeed. So take epsilon bigger than 0. In the Lindeberg condition, we have something like x square on the set x is bigger than epsilon. And I can bound this because here I only consider the x's which are bigger than epsilon. I can bound it like this: x to the power t plus 2 plus delta divided by epsilon to the power of delta, indicator x is bigger than epsilon. So why is that? So when you multiply this here to the other side, you have something to the power of 2, okay, that's the same, and something to the power of delta. But on the event that x is bigger than epsilon, x to the power of delta is the epsilon to the power of delta is smaller than x to the power of delta. So that's the reason why I have the inequality sign in this direction. And of course, leaving out the indicator function just makes this bigger here. And using this, let's just assume that the x and j's have expectation 0 for simplicity, then I need for the Lindeberg condition the expectation of x and j square on the event x and j bigger than epsilon. I can use the inequality here, so it's bound from above by sum j from 1 to mn, expectation of x and j, x and j to the power of 2 plus delta divided by epsilon to the power of delta. If the Lyapunov condition holds, this here converges to 0, and dividing by epsilon to the power of delta doesn't change anything. So as n goes to infinity, this here converges to 0, which means we just have showed that the Lyapunov condition implies the Lindeberg condition. And now let's come to the proof of the Lindeberg-Feller theorem. So here it is. What do I need to do? So the interesting bit, as we said, is the direction from 2 to 1. And I'm going to do this using characteristic functions. And since I'm using characteristic functions, I will have to deal with the characteristic function of the sum here, which is the product of the characteristic functions of the x and j's. And I will also have an intermediate step. I will take, as I write here, I will have the x and j's, and I will have the z and j's, and the z and j's have the same mean and the same variances. And I will basically show that the characteristic function of the sum of the x and j's converges to the characteristic function of the sum of the z and j's. And the sum of the z and j's, because sigma and j square converge in sum to sigma square, that will give me that the sum of the z and j's converge weakly anyway to z. So I will need that the characteristic function of the sum of the x and j's, which is a product of some complex numbers, converges to the product of the characteristic function of the z and j's, which is the product of other characteristic complex numbers. I will have here two preliminary lemmas, which I'm not going to show. They're basic estimates for complex number calculations. They are in the manuscript. So the first one is the difference of the products is less or equal than the sum of the absolute values of the differences. Okay. And the second one is something which you may use also somewhere else. So as you know, e to the it can be written as a Taylor series, which is the Taylor series exactly looking like this here, but going up to infinity. But when you stop at n, what's the error you're doing? So it's bounds the error you're doing, and that's this here. So there's something t to the power n and minimum t to the power n plus 1. And if t is smaller than 1, this here is smaller usually. And if t is bigger, then, if t is bigger, this here is bigger. And if t is less than 1, then this is bigger. Okay. But I guess you can believe that there must be some estimate when you break the Taylor series of the exponential distribution after the nth term. Okay, so these are the two preliminary things. And what I will also do, I will write something a is approximately smaller than b if it's smaller than some constant times b. And the constant, of course, must not depend on any n or something else. Because I want to show that the b here, which depends on n, converges to 0. And if c does not depend on n, then a also converges to 0. That's how I want to use this. Okay, we have two characteristic functions, the psi nj's and the psi tilde nj's. Without the tilde, I have the x's. With the tilde, I have the z's, which have the right distribution already. So let's now get started with the theorem, so the proof of the central limit theorem. First, let me make the direction 2 implies 1. And let me take some epsilon bigger than 0. And first, I like to start with the trivial part, which is this here. So since they are equivalent, I also have to show the second half of 1 from 2. So this sub over all j sigma nj square, I can bound this by epsilon square plus, well, what's sigma and j? That's the expectation of x and j square. And I'm splitting x and j bigger than epsilon and x and j smaller than epsilon. For smaller than epsilon, I can have the bound epsilon square for the x and j square. And I still need this sub over all j's. Okay, there's a trivial bound that positive numbers, for positive numbers, I can bound the sub by the sum. And I'm doing this, of course, because the Lindeberg conditions, the Lindeberg condition gives me something about this sum here. So this sum here converges to 0. So this converges to 0. This here is epsilon, as in to epsilon square. And now I've shown that this supremum here, which probably could use a square, and it has a square, converges to something smaller than epsilon square that holds for all epsilon, which means it converges to 0. And that's exactly what I have to show here. Okay, that was an exercise and maybe not too interesting. So let's come to the interesting bit, which is the convergence from here to here. So I said I'm doing this using characteristic functions. So on the one hand, I have the characteristic function of the sum of the x and j's, which is the product of psi and j of t's. And I'm subtracting, because I want to converge this to 0, the characteristic function of the sum of the z and j's, that was psi and j tilde of t. And I'm done if I have shown that as n goes to infinity, this difference here converges to 0. First of all, well, we had the first preliminary result that the difference of the products is bounded from above by the sum of the differences. So this here is less or equal than the sum of psi and j of t minus psi and j tilde of t. And I'm using a trick now, which is writing something in between here, subtracting and adding again, and then splitting the absolute value. So I have to be a bit careful with my space here. Some like this here, psi and j of t minus, and then I use the Taylor series approximation of the exponential up to second order, minus 1 plus 1/2 t square sigma nj square plus the sum, well, and here I'm doing psi and j tilde of t minus 1 plus 1/2 t square sigma n square. So this inequality, what happened? I wrote minus this thing here plus this thing here, and then I split the absolute value. That's all what happened here. And I'm bounding this from above using the triangle inequality. And now, okay, here, what's written here is an expectation of e to the I t x. And I'm subtracting the second term in the Taylor series approximation. And it's exactly something like this here, with an expectation in front, and I can bound it like this here. So basically what it is, t to the power of 2 minimum t to the power of 3, right? Up to some constant, which doesn't interest me too much, because I only want to show convergence to 0. So I have j from 1 to mn, and I have the minimum of the second and third moment. I can write it like this here. And the other thing, well, that's similar. But I just write it down, right? Yeah, I will just write it down as it was. Here I know that the psi and j tilde is something which I can really compute. E to the minus 1/2 sigma n j square t square minus 1 plus 1/2 t square sigma n square, like so. And now I have to show that this term converges to 0 and this term converges to 0, both using, the first one using the Lindeberg condition, and the second one should do it on its own. And I have it here now. So I had this term here. So how can I show that this converges to 0? I take some epsilon, and then I can again split this thing here on the event that x and j is smaller than epsilon. I can bound this thing here by epsilon, which is this epsilon here, and it stays x and j square. So I have the sum over these here. And I also get this, which is exactly the Lindeberg condition, which tells me that the second part here converges to 0. And the first one, well, the sum here by assumption converges to 1, and epsilon stays, but epsilon was arbitrary, which means that this here converges to 0. And the second thing is, well, this here is exactly the second term in the Taylor series approximation of this function here. And the error I'm doing, well, the next term would be something with sigma nj to the 4. And up to some constants, that's the order of this thing here. And from this power of 4, I do two things. A power of 2 here, a bound from above that by the supremum. And the sigma nj square stays. And the sum of these squares here converges to sigma square. So I have something which is constant times something which converges to 0, because I have assumed, because I have already shown that this here holds, because in the first part we had that this here implies what we just need, and it also converges to 0. Which now means we are done showing the central limit theorem, because we started with this, we proved the second property here, and then we showed that the characteristic functions of the sum of the x and j's converge to the characteristic function of x, using, well, first splitting some things here, ending up with these two terms, and both converge to 0. Okay, that was the interesting part. Let me also say a bit about the not so interesting part, which is 1 implies 2. Yeah, so there's some calculations involved. I will not do that very precisely here, just approximately. So let me start here. So psi and j of t, that's the characteristic function of x and j. X and j is something small because only the sum converges to something, and the sum of many of these things. So x and j is something small. And if x and j is something small, the characteristic function is close to 1. Well, that's I'm going to use here. And yeah, I can write it like this here, the characteristic function and the real part of it. What does the real part of it do? The real part of the expectation is the expectation of the cosine here of txn on the one hand. Minus 1 I just write down, and then the psi here is close to 1, as we said. And looking at the next term, I have the logarithm here of psi and j of t. And the logarithm of the psi and j of t, so psi and g is close to 1. So write psi and j of t as 1 plus psi and j of t minus 1. So 1 plus psi and j minus 1. And this here is small. Psi equals this here. The logarithm of 1 plus something small is the small thing, which is the reason why this logarithm is close to psi and j of t minus 1. And the nice thing about this argument is that since I can use 1, I know that there's a convergence of the characteristic functions to the characteristic function of the normal distribution. So this sum here converges to e to the minus t squared half, which means the logarithm of it converges to minus t squared half. Okay, so why is this useful? So here there's this funny cosine function. So why is this useful? Because you can say, well, assume that theta is something small, then the cosine of theta is approximately 1 minus theta squared over 2. Or in a picture, that's the cosine. The minus 1 minus theta squared over 2 is this parabola here. And that's the cosine. So for small x, that's approximately the same. So I can use this approximation. So 1 minus cosine is 1 minus cosine is approximately theta squared over 2, which means if I have the cosine here, okay, I have another restriction here that x and j is not too small, but well, still small, that the approximation here still holds. 1 minus cosine is approximately theta square. So I have this here, and that's exactly what I want to have because I want to say something about the Libyapunov condition, which involves this kind of expectation. As I explained to you, this approximately here holds. I can bound this by neglecting the minus cosine. I end up with only the probability of the event, which I'm bound to here. By using a standard Chebyshev inequality, the probability that x is bigger than epsilon is bound from above by sigma nj square divided by epsilon square, like this here. Which is, so the sum we assume it converges to 1, 2 divided by epsilon squared t square. But as you see, on this side here, there is now t, which means I can now let go t goes to infinity here. T goes to infinity, so this converges here to 0, which means that this here must be 0. And that's what we wanted to show. Epsilon was arbitrary, and we have shown that this here converges to 0. Okay, and this also shows that 1 implies 2. Okay, that was it for the central limit theorem. And next time we are doing something similar. We are studying, I think, multidimensional convergence results. See you then.